Hi, in this video we will talk about dynamic programming. Dynamic programming is a technique similar to the greedy or brute force or divide and conquer. It's a technique to design algorithms. So in the greedy, we saw that in the greedy, like we order the input and try to build the solution incrementally. For example, for the interval scheduling problem, we order the intervals based on the interval that finish first, and then we try to select the interval and then delete all the conflicting and then the selecting next interval and so on. So this is greedy, like we build the solution incrementally. We order the input and then we build the solution incrementally. Divide and conquer, we have problem, we divide it into two smaller problem, we try to solve both problem recursively and then we combine the solution. So this is the divide and conquer techniques. For the dynamic programming, it's something different. We have some recursion here. So we break up the problem into series of overlapping sub-problems. So we have sub-problems, but in a different way that we will see in this video. So dynamic programming was founded in 1950. Something about dynamic programming, the name is a little bit confusing. So it's not really related to the technique, and it has some reason in the history, but anyway, so we will learn about the technique itself. It has many applications, many algorithms in many fields are depending on dynamic programming, and today we will take just one example or two problems that use dynamic programming. The first one is weighted interval scheduling. We know what's interval scheduling, we studied it before, but today we have to add some weights to the intervals. So the interval scheduling is that we have some intervals starting from some time and ending at some times, and we need to select the intervals that does not conflict. For example, this interval, if I choose this, I can choose this and this, they are not conflicting. But my goal is to select the interval that has the maximum total weights. So I have some intervals with starting time, finishing time, and every interval has a value. I want to maximize the total value of the selected intervals. So two jobs are compatible if they don't overlap. My goal is to find the maximum weight subset of mutually compatible jobs. Like for example, in this example, if I say there are some values here, the value here is 1, 5, 2, 3, 10, 2, 1, 5. So the best solution for this is to pick this important interval and this. So the total weight is 10 plus 5, which is 15. So you can see that if we apply greedy, or also we can add this job, by the way. So actually it's 5 plus 10 plus 5, it's 20, because this job and this job are not conflicting. So if we want to apply the greedy algorithm unfortunately will not work. And the reason, this example, if we took two jobs, one is long, starting at time 0, and the weight is high, the value is high, and one is short, and the weight is 1. So the greedy algorithm will order the jobs, the intervals based on the interval that finish first. So the greedy will select this job first and then delete all the conflicting jobs, but then I get a value of 1, which is very bad, because the optimal is to select the other interval and get a value of a very high value. So the greedy is not a good technique for the weighted interval scheduling. It's very good technique for interval scheduling when we don't have weight, but not for the weighted version. Now, how to solve the weighted interval scheduling? We will use for sure dynamic programming. Before the dynamic programming, let us define some notation. First, we want to order the jobs based on the finishing time. So, because this interval, sorry, sometimes I say about interval job. If this interval finish first, we will number it with the number 1. And then next one, this finish next, 2, 3, 4, 5, 6, and so on. So this is the numbering I will use based on the finishing time of the jobs. Then I will define some notion called Pj. Pj is the largest index that are less than j, such that job I is compatible with j. Let me give you example. If I want to know what is P6, I will look to the all jobs that are before 6. So this job is not compatible. This is not compatible. This is not compatible. These two jobs are compatible. Okay. I will select the largest index. Which one is larger? 1 or 2? 2. So the largest index is 2. This is B6. So if I want to say what is B4, I look to all the jobs that finish before 4. So these are not conflicting. I only have one job, so I don't have choice. I take the index of this job. If I want to know B5, it's all the jobs that are finishing before 5, but I don't have jobs that finish before 5, so it's 0. And if I want to know what's B8, what's the job that finish, these jobs finish before 8 and the largest index is 5. So this is the definition of Bj. As we said, B8 is 5, as we saw. B7, we look to the jobs that finish before 7. Start, we have these jobs, we take the largest index is 3. B2, we look to all jobs that finish before 2, and we don't have any job, so it's 0. So this is the definition of Bj. We will use it in the dynamic programming. So now we will have another notation. It's optj. Optj is the value of the optimal solution of the problem consisting of job requests from 1 to j. So let me go back to the example and I tell you what's optj. Let me delete. So we have another notation called optj. If I say opt2, the meaning of opt2, imagine you have only job 1 and job 2. So you have all the jobs from 1 up to j, which is 2 in this case. So if you have 1 and 2, what's the optimal? Either you select this one or this one, depends on the value, on the weight. Imagine the weight here is 3 and the weight here is 5. So we will select this job and the weight will be 5. So this is the optj. Imagine I take another example. What's opt5? Opt5 means you have all the jobs from 1 to 5 and you want to compute the optimal. So let's say the values here are 1, 5, 1, 3, 2. So I think the optimal for this collection of job is to take this job 5. Yes, in this case opt 5 is 5. So the optimal for this instance is to select only this job because it has larger weight. But anyway, we just discussed this notation. We will see how to compute the optimal weighted interval scheduling. So this is the definition of opt-j. Now, here come the dynamic programming. So we want to find some recursive formula, something similar to this. And to find such, we want to study the following cases. The optimal assignment have two choices, either to select job J or not to select job J. So if I decided to select job J, then I have to collect the profit. Because I select job J, then I have to take the profit and add it to the optimal. And then I cannot use all the incompatible jobs with job J. So I have to delete all the jobs that contradict with J. So I only need to look to the jobs between 1 and Bj. So to compute the optimal, if I select the job, it will be Vj plus optimal of the previous instance, which is Bj. Why Bj? Because Bj tell me which job are not which previous jobs are not contradicting with J. So if I find the optimal of these jobs in the previous, I add Vj, then this is the optimal. Let me go back to the example again. So imagine J is 5. Or let's say maybe 7 is a good example. Imagine J is 7. So I will consider the jobs from 1 to 7. Like 8, I will not consider it yet. So I have two options, like opt 7. I have two options, either to select job 7 or not. Imagine you want to select it. If you select it, then you add the value of this job. You look to the weight and you will add it. And you will delete all the conflicting jobs. You will only consider these 3 jobs. But these 3 jobs are B7. You remember? B7 is 3. So it's V7 plus opt for the first 3 jobs, or opt for Bj. Okay, so this is exactly the first case. If you look here, the first case, we add Vg plus opt to the Bg. What is the second case? The second case, if opt does not select job J, in this case, I will not add the value of this job. I will just look to the previous jobs, which are the jobs from 1 to J minus 1. So I only look to the optimal J minus 1, which are the optimal value from the jobs from 1 to J minus 1. So I will look which one is maximum, and I will consider it as opt J. So if you see, it's kind of recursive formula. Opt J depends on opt J minus 1 and some previous opt as well. So it depends on 2 values. And for sure, if J is 0, if you don't have any job or an interval, then the value is 0. So this is the recursive formula that you will get, and based on this, you will build the dynamic programming. So you can just program it like this, like the input is this input of the problem, starting and finishing time and the value and the number of jobs, and then you sort the jobs based in the finishing time, and then you compute B1 to Bn, and then you do some recursive formula, compute opt j, but this will take exponential time, because imagine you want to compute opt 8. To compute opt 8 you need to compute opt 7 and let's say maybe opt 6. To compute opt 7 maybe you need to compute opt 6 and opt 4, something like this. So it will be like 3 and it will need exponential time. So something like this. To compute 5, so let's see, to compute opt 5, what is opt 5? So we have two options. Either to select 5, in this case it will be maximum v5 plus opt b5. What's b5 in this case? b5 is these jobs from 1 to 3. So it will be opt 3 v5. We take this job, we delete this because not compatible, and we compute the optimal of this. Or we just decide not to take this job, then in this case it's opt 4. So to compute opt 5, we need to compute opt 3 and opt 4. To compute opt 4, you need opt 3 and opt 2. To compute opt 3, you need opt 2 and 2. If we keep computing, you see, like for example, opt 2, you compute many times. Opt 1, you compute many times. So that's why we get exponential. So what's the solution for this? There are two solutions. The first one is just to store the value in the array so that we don't compute it again and again. And another value is just to do bottom up, like this example. It's bottom up programming. So you start here, you sort the jobs and you compute bi to bn, and then you do this. You start by m0, like it's opt 0. Opt 0 is 0, and then you go to opt 1. Opt 1, it has some recursive formula, it depends on the previous opt, so you can compute it. And then you compute opt 2, previous, and so on. By doing this recursive formula, then you compute all the jobs from 0 till opt n. Opt n, you are considering all the jobs from 1 to n, so you find the optimal solution. What's the running time of this algorithm? So because we need to sort here, it's n log n, and here we just have n. So in total we have n log n, which is very efficient than exponential. So this is just explanation of what I said before. Here we need n log n to sort, and then we need big O of n, so the total will be big O of n log n. So this was about dynamic programming. The core of the dynamic programming is to find this recursive. Now let me do some example with you about dynamic programming. Should I use this example? Yes. Let me use this example. But for this example, I need to add some weights. So let's assume the weight are the same as these numbers, okay, for simplicity. So how to solve this problem like in dynamic programming? First, I compute opt 0. Opt 0 is 0, right? Then we compute opt 1. Opt 1, this one, will be the maximum of, if we decided to take 1, it will be v1, the value of 1, plus the opt of previous jobs that are not conflicting. In this case, we don't have such jobs, so it's opt0. Or we decide not to take this one, and this, then it's opt0. So opt0 is 0, opt0 is 0, so v1 is 1. So which one is larger, v1 plus 0 or 0? For sure it's 1 plus 0, so opt1 is 1. Now let's compute opt2. We have two choices, maximum between two things. The first thing is that we decide to take this, so it will be v2 plus opt the previous non-conflicting jobs, or b2. b2 is 0, so it will be opt0. Or we decide not to take it, then it's opt1. So opt1 is 1, v2 is 2, opt0 is 0. So which one is better, 2 plus 0 or 1? For sure it's 2 plus 0, so opt2 is 2. This means that the optimal for these two is to choose this one, and then you will get a value of 2. Don't choose this one, and then otherwise you will get a value of 1. If you keep doing the same, you will get at the end opt8, and it will be the solution for this problem. So this was about dynamic programming. I hope it's clear, and see you in the next video.